Okay, let's get started. I'm going to go over Unit 1 review answering. So I'm going to go ahead and go through that. Let me first get started. Okay, so first thing first, this question is talking about average atomic mass of Re. So when you find an average atomic mass of Re, right? So the regular Re versus the Re specific one, that is gonna be equal to mass of Re specific one. So in this case, we're gonna look for Re 185 and then time percentage, whatever that was, right? That, and then now we gonna add it with the other isotope. So in this case, the other isotope is 187. So we're gonna say mass Re 187, and then we're gonna say time percent of that. Okay, so let's go ahead and read it. So the Re with the average mass of this. So you know the average mass was 186.207 is AMU. I'm not gonna write the unit because just so you know that all the mass is gonna end up with AMU in this case, so we're just gonna leave it alone. Mass of 185, let's say. Re 187 is this percent abundance and then 187 mass. So in this case, you only have 187. We don't have 185. In fact, you are looking for 185. So we're gonna say, we're just gonna leave it as mass Re 185 time percentage. This case, you do know the percentage. Percentage is out of 100. Is 187 is 62.60. We'll just do 100 minus, or you can do 1 minus 0.626. So we're gonna get at 0.374. Again, this is come from 1 minus 0.6260. 0.6260 is this one, in case you are not sure of. Anyway, plus mass, we do know this one, 186.956, and then time the percentage, which is 0.626. Okay, so then what you just need to do is you just need to do math manipulations. So I hope you know how to do math manipulations. So I'm just gonna go ahead and do that. I'm gonna multiply it, go subtract it to this, and then divide it by that. Okay, so just in case, 186.207 minus 186.956 times 0.626. We're gonna divide it by 0.374. When I get there, since because you're also adding and subtracting, we are gonna go with the decimal. So that means this is a 3 decimal places. So 184.953, and then we're gonna say this is AMU. Okay, don't forget the unit. If you don't have a unit, you're gonna lose point. All right, let's go ahead and do the next one. Using periodic table compound which has higher percent of carbon. This one actually, you don't need to do calculation. You're just gonna say it, explain it, what's going on. So in C2H2, basically percent mass of carbon is basically 1-to-1 ratios, right? Mass of carbon, basically, okay, I'll just, this is kind of more like a multiple choice question, basically. So I'm just gonna go ahead and explain it. C2H2 is basically empirical formula. Is CH, basically meaning that is C2H2 ratio or percentage is basically 1-to-1 ratio with carbon and hydrogen versus CH4. You can see that the ratio is 1 carbon with a 4 hydrogen, basically. So therefore, percent of carbon is higher in a C2H2. Okay. Now, like I said, it is kind of more or less of a multiple choice question. Possibly that's gonna pop up us. That's usually what it is. They usually don't ask you explain it. Now, if they ask you to explain it, you can always calculate it. So, for example, I'm gonna say mass of carbon, which is 12.01 divided by 12.01 plus the hydrogen, which is 1.01, versus 12.01 divided by 12.01 plus 1.01 times 4. So that's the difference. Okay, moving on. So this now we're asking for actual percent difference. What is the percent of carbon? So we have to now calculate what I was just saying earlier, right? So let's go ahead and try to calculate each one. Okay, I'm just copying and pasting so that I don't have to write all that basically. So let's say it's gonna be equal to percent of carbon 12.01. In this case, remember there's two of them, so we're gonna just say time 2, and that is on the top, right? And then that is gonna be divided by, right? If you want to know, 12.01 times 2 plus 1.01 times 2, right? I just put the extra parentheses so that you can see, and then when you finish, you're gonna multiply by 100 to get a percentage, right? Whatever the answer is, time 100, 100, and then you're gonna get percentage. Okay. We're gonna do the same thing for this, except we're gonna do for the CH4. So let's see. Oh, wait, not there. Need to tweak a couple of things. So for example, this is just 12.01, nothing else, because just one C, right? Same thing, this is just 12.01, nothing else, because just one C. But we're gonna say there is a full right there. That's pretty much what we're doing. Okay, so let's see. 12.01 times 2. 1.01 times 2. Let's say we're gonna get this at 0.92. Well, in terms of percentages, how to round it, this one doesn't quite tell you because there's no number given except for the periodic table. So for the sake of them, I'm just gonna do full suffix, or we end up with a 2 decimal at the end. So 92.24. And then we have, let's see, what are we gonna get? That is gonna be 74, 0.7482. So that means 74.82 percentage. Okay, let's continue to the next one. Copper to carbonate is heated and decomposes. If 5.0 gram of copper is decomposed, how many gram of? Okay, this is a little train track that we did. I'm just gonna go ahead and do that little train track because it's a little bit easier for us to visualize. You don't, again, on the test, you don't have to do train track. You can just do multiplications, symbols, if it's easier for you. Okay, so again, I'm just using it as organization. Gram CuCO3. Okay, so what you're gonna do next is you're gonna to convert it until you end up getting CuO. So that's pretty much what you're doing. So again, let's keep going until we end up with CuO as a mass. Okay, so anyway, so let's first convert gram to mole. That is gonna be 1 mole because we know, because it is molar mass. Now here we're gonna compare mole to mole. That is not gonna be 1. Actually it is 1 in this case because coefficient is 1, but not gonna be 1 all the time because it is depend on the questions. And then we're gonna do that. So anyway, if you need to pause, skip over, do that. I'm just gonna have to figure out the mass first. CuCO3, 63.55 plus 12.01 plus 016 times 3. So 123.56. Okay, CuO. That is gonna be 79.55 times 5 divided by 123.56. We're gonna get at 3.21. 3.21. Okay, so we're just gonna say 3.2 grams of CuO because I'm rounding according to the question. Right. Okay, let's move on. So, what is the mass of Cu in a CuO? Use no conversion. So pretty much we're talking about the periodic tables. What is the mass of Cu in a CuO? Okay, so mass of Cu in a CuO. That question is now a little bit strange. So let's go ahead and do that. Find the mass of Cu in a CuO. So yeah, let's go ahead and find it. So in 1 mole Cu, we're gonna have 1 mole C, and then go from there. Okay. So let's go ahead and figure that one out. So again, we're gonna need to try get a little bit of this first. I'm just gonna copy up so that we're not rewriting the table part. So we're gonna use this one. But in this case, we do have a known conversion that we need to convert to. Okay. So yeah, there's quite a few that we kind of need to do. Because you have the mass of CuO. Now we want to figure out what is the mass of Cu, so to speak. So we need to know that in 1 mole of CuO, we have 1 mole of Cu. Okay. So why I'm saying it is because we do need to convert the CuO into Cu, basically. So first thing first is we do have a molar mass, which is 79.55 gram of CuO. We're just gonna convert it to 1 mole of CuO. Notice that I kind of half did the other one first. That's fine. As long as all the unit cross out, we're good. Mole of Cu, and then you're gonna have mole of gram of Cu, which is 63.55. Okay. Gram Cu. Okay. Again, notice how the unit kind of work. Again, this is why I want student. Okay, hold on. That's not what I was doing. This is again. This is why I want student to cross out the um, the unit. Okay, so I kind of forgot what is the format for this one. Oh, shift. Yes. Okay, so again, right. Oh, not this one yet. It's this one. Right, these two units go away with each other. This unit go away with this unit. This then go away with this unit. So you can kind of see what's happening. So let's see, times 63.55 divided by 79.55. We're going to get at 2.57 or 2.6 gram of Cu. Okay, so that's what we're going to get as our answer for this one. Okay, next one. Calculate the mass percent of carbon in a hydrate of the solid that has this. Again, we just want to find percent of carbon, so we are finding molar mass of the whole thing, basically. So we're gonna say mass of carbon divided by mass of this whole thing, and of course time 100 as always. All right, so let's go ahead and do that. Now notice that there is 2 carbons, so 12.01 times 2. That's first. Oh, I'm not typing that correctly. So that's for the carbons on the top, right? And then we're gonna say divided by, we have a whole lots of them to do. So let's see, let's start with beryllium. Beryllium is 9.01 plus carbons 12.01 times 2 plus oxygen is 16.000, which is 16 times 4 plus 3 water. So 3 times. If you know that mass of water, you can just go ahead and do that, or you can start with the hydrogen, then oxygen. Either way is fine. So if you know it, that would be the 18.02 of water, so which is what I just did. And then when you finish, don't forget to multiply by 100 so that you get your percentage. So overall, we're gonna get, let's say, 9.01, 12.01. So we're gonna get 15.897, so 15.90%. Okay, so that would be the mass percent of carbon in this hydrate. Okay, mass that is to be formed. We're just doing reaction, so we just have to figure out what's going on. Basically, we just want to know how much percentage is water that is coming out, how much is being left. So this is still a stoichiometry, right? So let me just go ahead and do that. Usual thing. A little bit easier for us to see. Okay, I'm just trying to format it. Okay, now again, formatting doesn't really matter. You don't have to format it this way. I'm just a little bit more crazy about formatting. So anyway, so let's go ahead and get started. We're gonna get started by this chemicals right here. Okay, so we got this gram of this, right? So what are we gonna do? Well, we gotta convert as usual gram to moles and then moles to grams. Okay, so that's pretty much it with the usual arrangement of things. So let's go ahead and do that. It's not gonna be this one. In fact, we do have a number from before, I believe, BECL C2O4H. Yeah, so we do have a number from up there. We just need to redo this. This is gonna be this bottom part of that. That is 151.09 gram. So that's what we have. And then, so we're gonna say that is equal to 1 mole, which is true of that. Again, it's not this. Just doesn't want to rewrite that. So now we need to do mole to mole. And I'm just gonna go ahead and put that 1 mole to 1 mole because I'm really running out of room. And then after that, we're gonna do mole to gram. Okay. And then that would be the gram of BeC2O4 without the water. So let me go ahead and see what would that be without the water. So that would be 97.03. So that would be BeC2O4 without the water. Okay. So yeah. So more or less, that's what we're doing. Right here, 1 to 1 is from the Be with the water hydrate to the Be without the water. So again, I'm not writing in full amount, which you should know how to do it. Okay, so anyway, let's go ahead and do that. 3.21 divided by 151.09. Okay. So we're gonna get 2.06, good enough, gram of BeC2O4. That's what it's gonna be produced. Again, some rounding is fine. Mass of carbons in this, again, so basically that is just this conversion. So we just want to know how much of this is a carbon. So again, you can just do normally this amount. Okay, now I'm gonna say time 2 mole of carbons in 1 mole, right? 1 mole of BeC2O4. Okay, so now once you finish, you also have to do grams to mole conversion, so that way you can get to gram to gram. So gram to mole conversion, gram is, we have it earlier, 97.03 gram BeC to O04. Okay, and then of course that is 1 mole of that. Okay, so now what's gonna happen next? Well, you gotta convert it to gram of carbon because it's a mass of carbon. So we do need to find the mass of carbon. So mass of carbon is 12.01 gram carbons, and that is gonna give me 1 mole of carbons. Okay, if you guys are curious, these is multiplications on each one, right? And then we're just multiplying in each one, like I said. And yeah, just trying to make it look like you're dividing. So normally when you're writing it, this is how you usually write them, right? Except I use a table to organize this, but that's what it is essentially. All right, okay, so let's go ahead and solve that mathematically. Again, there could be some rounding error, which is that's okay. As long as you get relatively close, we're good. Okay, so we're gonna get 1, 0 gram of carbon. Okay, what percentage of acetic acids is, oh wait, the percent acetic acids, okay, so they want more molecular formula. Okay, so it's easy. Empirical formula, then molecular formula. So step by step. First step, percent is a gram. So that's what we're gonna do. So each percent is each gram, and then gram to mole ratios, and then yeah. So let's see, 39.9 gram of carbons. Okay, we got, I'm gonna just write ratios. This is easier when you do it on a pencil and paper than to type it in a calculator. I mean to type it in a here, in a computer. But either way, it's fine. Just make sure you are aware of what you're doing. 53.4 gram of O. Next step, convert them to mole, divided by the molar mass. Okay, divide by molar mass. So we're gonna go ahead and divide. So this one will be divided by 12.01. Okay, we're gonna divide it by 1.01, and then we're gonna divide it by 16. So again, in case you're wondering, I'm just going ahead and dividing these by each individually. We're gonna get, okay, this part I like to keep a little bit more number so that we don't have the rounding happening. So I just keep a little bit more number, like I said, just to make things a little bit easier. 6.53465. Okay, this is a mole of H, and then 3.3375 mole of O. Next, divide them by the lowest number. So in this case, the lowest one happen to be carbon. So let's divide all of them by lowest one. So we are now dividing each one by this number. Okay. I just want to add it a little bit as to like how to find it. So just in case you're wondering, this is how you're gonna find it. This is a way to find empirical formula, right? So okay, is this way. Molecular formula then is you find the mass ratios, and then you get the molecular formula. So you'll see in a bit. So this is where we're at right now. You divide it by the smallest, so that's what we're gonna be doing. So obviously this is gonna be 1, right? 1C versus, let's see what's happening. that last one should be about 1 also. Let me see how close it is. So the last one is 1.004. Or 1.005. Either way, doesn't matter. That just, oh, sorry. I just go octave higher. I'm so excited. All right, 6.5346653. Okay, 3.32223. So that's 1.9669. So what does that mean? That means 2 of H. So you're going to round it now. So we're going to say 1C, 2H, and then 1O. So you're going to have it as CH2O. By the way, you will see that this is correct, but this is empirical formula to find molecular formula. So let me go ahead and do this. We define molecular formula, find empirical formula, mass divided by, given molecular mass divided by find empirical formula mass, and then the next step is multiply the factor to the empirical formula. Okay, so that's how you're gonna get it. Okay, so let's go ahead and see. So we have CH2O3. CH2O. I don't know what I'm saying. So we're gonna do formula mass first. Which is we're gonna do C 12.01 plus H 1.01 times 2 plus O is 16. So we're gonna get 30.03. Okay. That is gram per mole. All right. So that's what we're gonna get. Or you can say AMU or 30.03 AMU. So which you will see you have a molar mass of 60. So 60 divided by 30.03 is approximately 2. So therefore, find molar formula is C2H4O2, and we will be correct. Okay, so that is the molecular formula. Because 2 times empirical formula. Okay, so again, way to solve this. Compaction analysis. Okay, this one need a little bit more stuff. You kind of have to do a lot, a little bit. Okay, let's continue on a hydrocarbon. So hydrocarbon sample with a mass of this. Okay, hydrocarbon is, unless they tell you, you don't know if there is a hydrogen, carbon, and oxygen, or it's just carbon and a hydrogen. Okay, so we're gonna say that CHO, some kind of CHO, plus O2, because that's a combustion. Combustion always do this. And then that's gonna give me CO2 plus H2O. Okay, so right now we know the amount of carbon, hydrocarbon, which is 11 gram, and then it is producing 33 gram of CO2. And if all the carbon initially present in a compound was carbon to carbon dioxide, what percent of carbon by mass is the hydrocarbon sample? So this is a little bit different from what I used to teach you. What I used to teach you was you can use these to figure out the percents of carbons and hydrogens, and then you go backtrack and find it. So here is the same idea. So what they were trying to say is all the carbon in a CHO is now can be found in the carbon dioxide. Okay, so first let's find out how much carbon is in a sample. That's what it is you have to do first. So that's what the question is saying. So I want to say mass of carbon is going to be equals to, coming from the carbon dioxide amount, which is 32 gram CO2. By the way, that is no. I wrote my O round. O should not be this. O should be this. Okay. So mass of CO2. Again, I don't want the CO2, so we're gonna say 1 mole CO2, which is gonna be divided by the mass of CO2, which is 44, I think. Yeah, 44.01 gram CO2. Okay, so now that we get it, we get the mole. And then now what we're gonna do is we need to convert that into mole of C. So you will see that 1 mole of C is in the oh my god, I wrote too far. 1 mole of CO2, right? And then afterward, you're gonna do mole to gram. So we're gonna say 1 mole of C is 12.01 gram of C. That will give me the mole of C. Okay, pretty much that's what we're doing. And like I said, that will give you the mole of what you're looking for. Okay, so pretty much that's what we were doing. Okay, just kind of like shifting a little bit. Hold on seconds. Okay, let's continue. So yeah, so pretty much that's what the question was saying. So the question said percent of carbon in a hydrocarbon. So whatever you have, you can just gonna divide it by 11 and then time 100, so that you get a percent of hydrocarbon. So first, let me figure out what is the other one is. 01, 12.01. That's gonna give you 9.07 equal. Oh my god, why am I doing spotlight search? That's not what I'm trying to do. 9.07. So that's what you're gonna have. And if you're doing twos, yeah, so you're just gonna keep it two specific than 9.1 gram of C. Okay, now what we're gonna do, like I said, we're gonna divide things up. So we're gonna say 9.2 divided by 11, and that is gonna give a certain number, and you're gonna multiply by 100 so that you get percentage. So this is 0.82, which is actually 82%. Do you have to write the one on the top, this part? You don't. This part just kind of more like for you to see. You don't. So actually, I'm going to delete that. This is all they were asking for. Okay. All right. So let's continue. So now the usual one we ask in class is a little bit harder, because the usual one we talk about it is you find each part. Okay. Okay, let's do 7. Elemental analysis, quantitative relationships, right? So mass is conserved, so remember that one. Okay. Do I have copper 2 chloride or copper 1 chloride? So basically you're doing empirical formula to figure out. 2 gram of NO copper chloride solution dissolves zincs, and 0.95 gram of copper solid is recovered as part of the solutions. First, let's write the chemical equation. Okay, we don't really know what is the chemical equation of a little bit, because we don't know what kind of copper chloride it is. So I'm gonna have 2 possible equations, right? So I'm gonna have 2 possible equations. So you start out with CuCl or CuCl2. Okay, so NO, and this is gonna dissolve zincs. Okay, so we're gonna say plus zinc, and then you're gonna get copper as a product. Basically, what they were trying to say is this is a single displacement. Zn is gonna take Cu spot, Cu is gonna come out. So Cu plus Zn. Now Zn, you need to know about Zn is plus 2, so therefore that's gonna be ZnCl2. Okay, so that means I gotta balance this. I'm gonna put 2 in the front of that, and now I need to put 2 in the front of that. Okay, or I have this, not An, Cn. Then you're gonna get Cu alone, and then we're gonna get okay, ZnCl2. So you have these two equations. So let's get started first. So anode sample is 2.00 gram. That's the anode samples and dissolve, and then we're gonna get copper of 0.95 gram copper solid recover, and we need to figure out what it is. So what I'm gonna do is you can assume that CuCl2 and then or CuCl, and then we're gonna try to find a percentage, and that can tell you what it is. So what I'm trying to say is this, right? So mass, okay, hold on a second. Percent of Cu, right? Percent mass of Cu is basically gonna to be equal to mass of Cu divided by mass of Cu copper chloride. I'm just gonna say that. Try not to confuse you because we don't know what chloride is. And then that's okay, it doesn't matter, time 100, right? So that's how you get a percentage, basically. So we can still do it this way and try to figure out what it is. So what they're trying to say is this percentage is not going to change. We already know the other two numbers, so let's try to figure out what that might be. Okay, that will be equal to 0.95 divided by 2, and of course time 100, right? So let me see what this is gonna give me. 0.95. Okay, so that will be 47.5%. 47.5%. Okay, so now what you can do is you can see percent of mass of Cu. Okay, so this time we're hypothetically finding in CuCl, and then we are also going to find in CuCl2. Okay, so this part would be CuCl2. This part just would be CuCl. Okay, so how are we going to do that? Well, this is the hypothetical. So this top one, this one, we get it from the question. This is from the questions, right? From given in questions, right? So that's what we get. These two periodic table. So we're gonna look from the periodic table for these two. Okay, so let's go ahead and figure out. So Cu is 63.55 divided by CuCl, 63.55 plus Cl, 35.45. Okay, and now of course over time 100. Okay, so 63.55, 63.55, 35.45. So we're gonna get that 64%, 64.19%. And then we're gonna do the same thing with this one, except it's a CuCl2. So that means down there, that will be time 2. So that's the different part, right? So that would get me different number. That would give me 47.266, so 27%. So if you look at the other one, it is closer to this one. So that means your sample is CuCl2. Okay, so that's what it is. Notice what they were trying to say. Your mass percentage is going to be the same, and it's depend on the type of chemical reaction. Okay, so again, originally we don't know if it was this or this. We really don't know. All we know is this is the given, and then from there we just kind of like go through and trying to figure out what is going on, and then you'll see that the percentage is matched with the CuCl2. Okay, let's go into the next one. Okay, write the electron configurations, orbital notations, and the noble gas configuration, and then for each ion, what electron are removed or added. Okay, I think this is a complete. This is what I was asking for anyway. So we're gonna do two of them. So, all right, I'm gonna have Mg and then Mg plus 2. Okay, let's try to be a little bit neat. For each one, we're gonna do complete. Okay, so let's kind of do that. So Mg is 3s2, so we know where it's gonna end it. 1s, hold on a second. 1s, 2, 2s, 2, 2p, 6, 3s, 2. Okay, Mg plus 2 is just gonna be essentially this, because it's gonna lose 3s electron, right? Lose 2 electrons in 3s orbital. Okay, now noble gas configurations, that would be Ne, and then you're just gonna have 3s2. Okay, now if you are looking for the orbital diagram, as we will ask orbital notations, orbital diagram. Okay, so orbital diagram, here is how you're gonna draw it. You're gonna say this is 3s, and then insert drawing new. Okay. Okay, arrow. That's all you're gonna see for the 3s2. Oh, that's a little hard to see. All right, let me redo this. Okay, yeah, that's a little bit better. Okay, so that's what it is. All right, let's continue. P and P minus 3. Um, doesn't matter if you do minus 3 or 3 minus. Let's start with P first. That's a 3p3. Okay, so essentially, I'm gonna copy this part for the P, because it's a 3p3, so just need to continue on. 3, 3p3. Okay, so again, Ne, 3s2, 3p3. So let's go ahead and see what's gonna happen. So I'm gonna need to do 3p. All right, so for the 3p, let's draw 3p. P has the 3 little subs orbital, so we do need to draw 3 little line, sort of. Yeah, I can draw straight. So those are for 3p. Okay, and then arrow. Yeah, we're gonna have up, up, up first. That's how you're gonna fill it, and if you need to fill more, you're gonna come back and down, down, down. So anyway, oopsie. So now what I'm gonna do is we're gonna make them bigger, and we're just gonna save that. And then I don't know why the arrows get shorter. I can make it taller again. Yeah, I don't know why this is get shorter as we goes. And how come like these are taller? They should be the same amount of tallness. because it just mean electrons are there. So anyway, I'm gonna assume it's a little better. Okay, so 3p3. Okay, so what's gonna happen? So essentially, for this one, it's just become 3p6. So what's happened is it's gained 3 electrons, right? And then you can say put them in 3p orbitals. Okay, let's continue to do these two. This one, I'll draw the picture for you guys. What did they look like? Also, okay. All right, Fe plus 2, Fe plus 3. You can also see a little bit why Fe has a multiple valence electron. It has to do with this. Okay, so Fe, let's see, 4s, 3d6. Okay, so I'm just copying this so that I can just continue writing there. So that would be a 4s to 3d6. Some people like to say 3d6 4s2. That is fine if you want to write it that way. I personally don't, but if you write it that way, it is also fine. Okay, so let's see. On the top is AR. So AR is the noble gas before that. So we're just shortcutting it. So this is what you get. Okay, so let's see what does this look like in drawing. So I'm going to have to draw 4s and I'm going to draw 3D. 4s2 is essentially the same thing as this picture. So I'm just going to rewrite this. Okay, so that's a 4s. Okay, 3D is a little bit different. So let's try to draw 3D. Okay. Okay, 1, 2, because 3D has 10. So we do need to draw 5 on this row. Okay, 5. So what's going to happen? I'm going to draw the arrows, just like always. 1, 2, 3. Pretend that they are straight. 4, 5, 6. Okay, so you have 3d6 happening. Okay, so I'm going to make them a little bit bolder. So you can see, yeah, I know these arrows aren't really straight. They're a little bit slanted. It's okay. Alright, I'm going to make them taller a little bit, just because you can see. Alright, we have these. Okay, these two happen to be too close. That's okay. Let me edit it. Make it move a little bit apart from each other. Okay. Alrighty. So So what's going to happen? Well, what's going to happen is, let's look at what's going to happen to Fe2 plus versus Fe3 plus. This is where it's kind of get interesting. Remember how we said that noble gas is the highest orbital S and P orbital? Exactly, that's what is going to happen to the Fe2 plus. So Fe2 plus, when you get to there, its configurations is just going to be that without the 4s, okay? Or you can see just this without the 4s, okay? So that would be Fe2 plus. So Fe2 plus would look like this, and if we were to look for the pictures, that would be what it's gonna look like in the 3D, and then it's gonna look like this. Now, basically then it's gonna lose 2 electrons from 4s orbitals. Okay, now how about Fe plus 3? Well, you see how there's an extra electron that's going down? That's what's gonna happen. it's gonna lose from 4s, and it's also gonna lose 1 from the 3D. Okay, so that's what is gonna happen. So Fe3 plus essentially is the same thing. It's just gonna lose 1 mole from 3D, so it's become 3D5. It's gonna become 3D5. And then let's try to edit this. Hopefully it doesn't change the other one. I'm gonna just delete this one. Okay, there you go. So 3D5. Okay, so it's gonna lose 2 electrons from the 4s and 1 electron from 3D. So that's what is gonna happen on the Fe3 plus. So this is why transition are a little bit funny, because they have extra d orbital. So sometimes not only just losing from their s orbital, they can also lose from d orbital. Now, when you're adding electron, the same thing. Not only they can add to the s and p, they can also add to the d orbital. So this is why you kind of get a little bit different things happening with the transitional elements. Okay, so anyway, so that is what is going on with Fe. So hopefully that makes sense. You're just losing electron a little bit differently. Okay, let's go to the next one. This one, sometimes AP will tell you, sometimes they won't. So I'm just go ahead and telling you right now. Isoelectric. Isoelectric mean that they all have the same number of electron. Okay, which are following iron is isoelectric with neon. So that means they have the same number of electron as neon. And then tell me why. So, well, really easy. I don't even need to do electron configurations. Or, oh my God, why keep coming down? Okay, so I don't even need to know electron configuration. All I need to do is count the electron. So we're gonna say Al plus 3. Okay, so that means plus means lose. So lose 3 electrons from Al atoms. Okay, so Al has basically, where's my Al? I just lost it. Al has 13 electrons. So Al plus 3 have 10 electrons. Okay. Now Cl minus, F minus, Na plus, and Ca plus. They're all the same thing. I'm not gonna write down the explanation for each one. Essentially, it is the same. If I have to write the explanations, you're just gonna say either lose or gain, and you just kind of make the mathematical formula. So for example, this one, Cl minus 2 is gonna gain 1 electron, right? Right, gain 1 electrons, right? So that means that, and then we know that Cl has the 17 electron. So now that means Cl minus 1 will have 18 electrons. Okay, so again, I'm not gonna go ahead and do each one. I'm just gonna tell you what is going on. F is minus is gonna be 10 electrons. Okay, and then Na plus 1 is gonna be also 10 electrons. And then Ca plus 2 is 18 electrons. Okay, now we know neon. Neon has 10 electrons. So therefore, who's isoelectric with it? F minus 1 and Na plus 1 are isoelectric with neon. Okay, now next one. If the photon or energy applied to the atom is this, kinetic energy or electron this, what is the ionization energy? we talked about this one before. This is a ball kicking analogy scenario. I'm just trying to see if you guys still remember it. So remember that the ditch, right, needs certain amount of energy for the ball to go up. You're gonna kick the ball, and then the ball will climb up the ditch, right? But if you kick it with enough energy, not only is come out of the ditch, it will also have more energy to move after it, right? So that's what is gonna happen. So anyway, so that's what you have to do for this question. So in case you don't know, photon energy minus IE, ionization energy, which is the gravity kind of thing, right, to get out of ditch. But in this case, it's the ionization energy because the not neutron, nucleus is holding onto the electron, right, protons, okay. But we usually just call that nucleus, and then kinetic energy. Okay, so let's go ahead and do that. So first of all, check the unit. If the unit are the same, you are allowed to do this. So 143.4 minus 114.8. So that should be easy. 143.4 minus 114.8. We're gonna get 28.6. Don't forget a unit. And don't get yourself invented with these questions. Okay, what determine each peak in a photoelectron spectrum? Okay, so take a look at the picture. If you haven't seen it yet, you have these peak. What tell you what the peak was? That is number of electrons. Okay, different in ionization energy part in PES graph for NE and AR is due to difference in what? Okay, well, why would they have different energy? Why would NE and AR would have different energy? Because they have different nuclear charge of the atom, okay? Because NE has 10 and AR has 18. So 1s is really gonna get pulled in AR versus NE. Chemical property, not really. PS don't graph chemical property. Atomic radii of the atoms, a little bit. The number of neutron in the atom, no, not really. Okay, so if this were only asking for one answers, I would go with the nuclear charge of the atom. But if this was saying what is all that stuff that is going over it, radius is also included because, right, the closer the electron are to the nucleus, the harder it is for them to move, basically. Okay, based on this PS, what do we have? 1s, 2s, 2p, 3s. Again, 3s2. So 3s2, that's a magnesium, Mg. Okay. Again, I'm not gonna write the explanations. If you don't know, you should write it down. But the explanation just earlier, just like how I said it, electron configuration, you're just counting 1s, 2s, 2p, 3s. Okay. I am not gonna do this part one, right? Because we have already talking about what's going on, what's happening, right? So OSSETE, because yeah. So you can see which one we're just saying valence electrons, where they are at, and then that should kind of tell us what happened. Okay, so let's go ahead and arrange this one. NASMGCLMP, smallest to the largest, and explain the trend. Again, first take a look at where they are in the periodic tables. So I'm gonna go ahead and mark them on my paper so that I can see a little bit better, and then we can go from there. Okay, so NA, we got it. S, we found it. MG next to each other. CL, MP. Okay, so then next to each other. If you look at it, it is just in the same row. So I'm just saying in the periodic table, you have Na, Mg, P, S, and then Cl. And then that's how you can say. And then if you go left to right, what do we know this? Going to the right side should be the smallest one. Okay, so in the row, okay, so I want you guys to remember is this same row, left to right. Okay, decreasing radius. Okay, and then explanation is due to increase in nuclear attractions due to more number of protons. Okay, think about that. So yeah, so that's what we're gonna do. Okay, so they said smallest to largest, so start with Cl, next is S, next is P, next is Mg, next is Na. Okay, you can say all of them have outermost electrons in, I think that's together, in n equal to 3. They are approximately the same distance from nucleus. However, Cl have the most number of proton, and then you can also put it in there, 17, right? As I don't know, 16. P has 15. Mg is 12, and Na has the least, right, 11 protons. Okay. The more protons means more nuclear attraction. Even greater nuclear charge. I'm gonna go ahead and bring in Coulomb. Yeah, I can never spell his name correct. I always put extra U there. Alright, Coulomb laws. The greater the charge, the more attraction, right, between the particles. What is this? Electrons are held the increased attraction results in smaller atomic radius. Okay. All right. Okay. Number 3, I have explained to you in class before. So essentially, you're just gonna explain it in terms of electron configurations and what is going on. Same thing with this part. Okay. Yeah, let's go ahead and continue. All right, just come back from lunch, so I'm gonna just continue. So this one, OSSETE, basically what they are is they are in the group, right, which is vertical, right? So in a group, when you go down the group, you know that radius is gonna increase, and then the reason is because the nucleus are farther away. And then we're gonna explain this in terms of energy level, electron configuration, or you can even say n equal to, which is the principal quantum number. So we're gonna say that. So we said n equal to 2 is closer to nucleus, then n equal to 3, 4, 5, 6. And then we can say the closer the electrons are, the closer the electrons are to the nucleus, right? Or let me just rewrite it the other way around, since we want it to be, yeah, it's okay. It's actually, you can say it this way, to the, so the more, the nuclear attraction increase. Okay, and then depending on the question, you might have to say Coulomb laws, right, and stuff like that. So according to Coulomb law, the increase right, or I can just say the increase in nuclear attraction the electrons pull closer, smaller atomic radius. Okay, let's look at this one. Okay, so T, E, S, S, E, and O, they're all -2. Pretty much they are in the same vertical grouping. So you will see the O is on the top, T is on the bottom. So we know which one is bigger, which one is smaller in the sense of where they are at. So again, you can use the electron configurations to tell. So anyway, so this O -2 is going to be smallest. We know that. Okay, so O -2 is gonna be less than S -2, which is gonna be less than SE -2, which is gonna be smaller than TE -2. O -2 is the smallest. Part of the reason why is we can say O -2. You can say okay, O -2 at -2 is smallest. Smallest its outermost electrons are in n equal to 2. Closest to the nucleus, and then you can say the rest kind of with the TE -2. So we're going to say TE -2 is largest because its outermost electrons are in 2, 3, 4, 5, 5p. So it is furthest away from the nucleus. And then we can say the closer electrons are to the nucleus, the more attraction between them. This decreases the atomic radius. Okay, so I'm just gonna keep it like that. I have talked about B already in class, so you can kind of take a look at it. I'm not gonna write for each one just because they are kind of similar. I compare the 2 plus and I compare the all the minuses, um, and then so you get this idea. So you should actually go back and talk about which one is bigger in a sense that you should go ahead and compare the whole thing. So I'm gonna say, let's see, Mg2 plus is the smallest, right? And then Na plus, and then the next one is Cl minus, and then S minus 2, right? So, and then this. Okay. So that's what you have pretty much in this question. Okay, let's kind of continue. Okay, this part, the same thing kind of. You're just gonna compare them where they're at. So let me see. We got V minus 5, S minus 2, and then Cl minus 1. Okay, and then K, and then Ca. Okay, you'll see that they all gonna to give you AR. They all gonna give you AR. So I'm gonna say, when I say all have the same number of electrons, which is the 18, but they have different number of protons. The bigger protons to electron ratios will result in bigger nuclear attractions and result in smaller atom. Okay. So result in a smaller atom. So therefore, V plus 5 is smallest. V plus 5 is smallest. 23 protons compared to 18 electrons. And CS minus 2 is largest. 16 protons compared to 18 electrons. Okay. The smaller proton to electron ratio will reach less nuclear attraction. So you can compare like that. Okay. So when you finish, you should definitely add it in to see which one's bigger. So they should be in order of as follow. Not gonna make it uppercase. So V5 CA plus 2 K plus and then CL minus 1 and then S minus 2. So smallest to largest radius. Okay, so explain ionization energy and different in IE1. So we can say that, right? So that's that, and we can say that it is easier to remove electrons from n equal to 3 than n equal to 2 further from nucleus. See, nucleus, lower nuclear attraction. Also, Na is neutral atom, and Na plus 1 is iron, right, with one less electron. The proton to electron ratios is higher in Na plus 1 as no nuclear attractions, harder need more energy to remove electron from Na plus 1. Okay. Again, you can just fix it to make these error like spellings or whatnot, right? Okay. So anyway, that is the next part. Again, that should be n electron. Okay. Explain the difference in IU1 of the metal and non-metal. Okay. So so in this case, we're only looking for the Na, Mg, and so on. So what can we say about metal versus non-metal? Okay, so let's take a look. Na versus, let's say, Cl or something. So if you look at it, Na, Mg, Al, Si, P, S, Cl, those are in the same period. So they're in the same row, but you can see that the nonmetals has a much higher ionization energy compared to the metal, right? In the same period, I mean row, right? Non-metal have higher IE than metal. Okay. Same period. Atoms in the same period have outermost electrons located in the same principal quantum number, which is what we're talking about, n equal to. Okay. So what does that mean by the same principal quantum number? Well, that means they are the outermost electrons are in similar distance from the nucleus, but within the same electrons compared to metal. The more protons in the nucleus will increase nuclear attraction, and thus electrons are held tighter, thus require more energy to remove electron from non-metal, higher IE in non-metal. Okay. Explain difference between ionization energy and electron affinity. IE is energy needed to remove electrons. Electron affinity is energy change associated with a something an electron. Okay, so I redid this part to add a little bit more information. So ionization energy is energy added, energy needed to remove an electron. Excuse me. As always, because you need energy, it is the endothermic, or you're gonna absorb the energy for this reaction or this process to happen. But on the other hand, electron affinity is an energy chain associated with accepting an electron. So here is an example equation, and this electron affinities, like I said, is energy chain. This is mostly negative number, which means exothermic or release energy. If you look in the graph here, it's a little bit harder to see. Let me zoom in so you can see a little bit better. You see that there's negative, and then if you go left to right, the negative number is supposed to be getting bigger. So like 48, negative 48, all the way to negative 195. So in a way, going left to right is increasing. Going down, it should be saying decreasing, but that's being said, you can see here it doesn't quite follow the trend for all of them. So for example, you can see that is left to right, electron affinity is increasing, or the bigger negative, but you can see that this one break the trend, right? Again, here breaking the trend here a little bit, breaking the trend here again, okay, increasing, break the trend again here, increasing again, break the trend here, and then increasing again. So you can see that electron affinity has a lot of like rule breaker, and it doesn't include the noble gas. Okay. Now for this question, here is what you need to know. Electron affinity increases, or the bigger negative, left to right, but did not include noble gas. Do not include the noble gas in there. And then there are many exceptions, like I was showing you. For example, SR doesn't follow the trend, CD doesn't follow the trend. So there are many exceptions to that trend, but you do not need to know them. However, you need to know how to explain it. So for example, they will say, comparing, let's say, Mg with Na. Mg has less electronegativity than Na. And then they might say, explain why. So in a case like that, you can say, because for the Na, right, if you're going to add electron, you're adding electron to the 3s. For the Mg, 3s is already filled. So if you're adding electron, you're going to add it into 3p. So 3p is a little bit higher energy level, therefore is gonna to be a little bit harder, right, to edit that electron, because the nucleus is not really attracted toward that electron, versus here the nucleus is more attracted to that electron, the extra electron that you're gonna add it here. So again, that's gonna make the difference. So you do need to add it something about that. Okay, so yeah, electrons always when in doubt, electron configurations that's gonna help you figure out how to say that, and also the proton number. Okay, next but not least, explain the difference between electron affinity for F versus Li. Take a look here. You can see here Li has less electron affinity compared to F. F is more has higher electron affinity. So first thing first, we're gonna say that F has higher electron affinity, right, compared to Li. Okay, now we're gonna say, well, let's think about where it sits in a periodic table. So let's take a look again. F versus Li. F is in 2p, Li is in a 3s. Okay, so again, you can kind of see where it's gonna come about. Okay, so first thing first, you want to know, I say F has higher electronegativity, electron affinity compared to Li. We can say more negative. Okay, so more negative, and the reason for its being more negative is as follow. The higher negative value, that's gonna indicate that nuclear force is stronger, and meaning that is able to attract electron effectively. Okay, so that's the idea. So, but how are we gonna answer it? Well, let's think about it for a second. So F is smaller atomic radius than Li, or you can say both F and Li outer electrons are located in n equal to 2. They are similar distance from nucleus or similar energy level. Nucleus. The F have more protons than Li. Okay, so F has more protons. By the way, F has 9 protons compared to Li, which is 3 protons. F have more the nuclear attraction, the nuclear attraction is stronger in F. The stronger nuclear force, the more attract, the easier or the more effectively it can attract electron, thus have higher electron affinity. Okay, something along the line of this, and I'm just gonna say that basically. That stronger nuclear force, nuclear attraction is stronger. The stronger nuclear force mean maybe strong. Okay, whatever. It's just the math part. Not math, English part. Okay, but anyway, that's what it is. What ion does the metal make? Metal tends to lose electron, form cation, positive ion, just in case. Non-metal tend to gain electron, form an ion which is negative ions. Okay, give example and explain the difference between the trend. Okay, the difference between the trend is metals only have one electron in the outermost shells, which means they are loosely held, they are easier to remove. Non-metals are they have more protons, they are smaller in general compared to their metal if they're in the same row, which is pretty much things that I wrote up here. Let me go back, comparing the metal and non-metal. So that's where you can kind of talk about it. Non-metal generally are easier at gaining, and metal are easier at losing because metal has lower IE, ionization energy, because they are kind of generally bigger. I'm not going to answer that one. Ionic character, that just meaning that is losing, right? The losing electrons, gaining electrons. So we're talking about ion character, and also that means that ion, right? Think about it, is a charged particle. So what does that mean? So ionic character, that means is easily conduct electricity. Okay. Basically, you can shock them. So think about like salt solution. Basically, you can put the probe in it and it will light up. It will conduct electricity. So you can say like salt solutions conduct electricity. Yeah. What element combined to make compounds? It is metal cation usually with non-metal anion. Okay, cation basically one gain, one lose, and then so that's what it is. Explain. Okay, I'm not gonna ask you much. Explain it just meaning that is compound is made out of ions. Ions has a different charges, plus and minus, and you can explain also metal tend to lose electron, therefore they form cations. Non-metal tend to gain electron, therefore they make anion. Okay, so that's the part about explaining. So what element tend to make compound? Metals, non-metal together. Okay. Alkaline is most reactive. Which alkaline and which halogens? Okay, so alkaline most reactive. Okay, alkaline, first of all, I want you guys to think the reason of what happened. Alkaline metal lose one electron. Okay, so that means it has low IE, more reactive, right? Because we're saying losing. The less energy you need to import to lose it, the better. So therefore, ionization energy lowest is francium, Fr. Okay, now let's talk about halogen. Halogens, let's talk about most reactive halogens is, well, before we do it, again, let's think about again. Halogens gain electron. Okay, halogen gain electron. So since halogen not gaining electron, okay, it doesn't want to lose it, it want to gain it. Bigger nuclear attraction is a better. Okay, think about smaller, bigger nuclear attraction. In this case, we're talking about fluorine is better. Okay, so that's pretty much it. Internal or atomic structure, including ion they are formed. So again, atomic structure would be like smaller size, bigger nuclear attraction. That's what we're talking about. So in this case, lower IE is not done. We want to talk in terms of nuclear attraction, weakest. Weakest nuclear attractions, biggest radius we're looking for, that is going to be better. This is bigger nuclear attraction, this is better. Okay, so that is pretty much it for this unit. Happy